Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into the heart of Apple's operating systems, Darwin and its XNU kernel. It's the foundation of Mac OS, iOS, and everything in between.
XNU, huh? I always thought it was some kind of secret code name. What exactly is it, and why should we care?
Well, the name itself is a bit of a joke. It stands for X is not Unix. It's a hybrid kernel, meaning it blends different approaches to operating system designs. It combines the Mach microkernel with elements of BSD Unix. This gives it both modularity and the performance needed for modern devices.
A hybrid kernel. So, it's like a Frankenstein's monster of operating systems? What were the original ingredients?
Haha, not quite a monster. Think of it more as a carefully crafted blend. The first ingredient is Mach, a microkernel developed at Carnegie Mellon University in the 80s. It focused on core functions like memory management, CPU scheduling, and interprocess communication, or IPC.
Okay, so Mach is the foundation. What about the BSD part?
BSD, or Berkeley Software Distribution, is a flavor of Unix known for its stability and POSIX compliance. It provides the higher-level services that users and applications interact with, like file systems, networking, and device drivers.
I see. So Mach handles the low-level stuff, and BSD provides the familiar Unix interface. How did these two come together in XNU?
That's where NextT Computer comes in. Steve Jobs, after leaving Apple, founded NextT and needed a modern OS for their workstations. They adopted Mach and layered a BSD Unix subsystem on top, creating NextStep. This kernel was later named XNU.
Ah, NextStep. That's the OS that Apple eventually acquired, right? So XNU came to Apple through the NextT acquisition?
Exactly. In 1996, Apple bought Next, bringing XNU and the engineering expertise of people like Avi Tevanian, one of the Mach's co-authors. This became the foundation for Mac OS X.
So what happened after Apple acquired Next? Did they just slap a new coat of paint on NextStep and call it Mac OS X?
Not at all. Apple integrated newer Mach and BSD technologies into XNU. They incorporated code from OSFMK 7.3, a Mach 3.0 kernel, and upgraded the BSD subsystem with $4.40 and free BSD code. They also replaced NextT's driver kit with IOKit, a new driver framework written in C++.
IOKit in C++. I thought everything in the kernel was written in C.
That's a common misconception. While the core kernel logic is in C, IOKit, which handles device drivers, is written in a restricted subset of C++. This was done to improve extensibility and code reuse.
Interesting. So Mac OS X was built on this hybrid kernel, combining Mach, BSD, and IOKit. What were some of the key milestones in its early development?
The first developer previews of Mac OS X came out in 1999, and the commercial debut, Mac OS X 10.0 Cheetah, was in 2001. Early milestones included Mac OS X 10.2 Jaguar, which brought IPv6 networking and a new MDNS responder service, and Mac OS X 10.3 Panther, which integrated free BSD5 kernel improvements.
And when did Apple officially certify OS X as a Unix system?
That happened with Mac OS X 10.4 Tiger in 2005. It became Unix 03 certified, meaning it conformed to the single Unix specification. Tiger also laid the groundwork for Intel Macs, which were announced later that year.
Ah, the switch to Intel. That must have been a huge undertaking. How did XNU handle that transition?
XNU's Mach foundations made it easier. Mach abstracted many low-level hardware details behind a portability layer. This allowed Apple to share much of the code between the PowerPC and x86 builds.
So XNU was able to adapt to the Intel architecture relatively smoothly. What about the move to 64-bit computing?
That came with Mac OS X 10.5 Leopard in 2007. Leopard introduced extensive 64-bit support, allowing the kernel itself to run in 64-bit mode. It also brought in security features like address space layout randomization, or ASLR, and the D-Trace instrumentation framework.
And that was also the time when the iPhone came out, right? How did XNU adapt to the mobile world?
Exactly. iPhone OS, later renamed iOS, was also built on Darwin. The kernel gained support for the ARM architecture and was modified for mobile devices. For example, it incorporated aggressive memory pressure handling and a JetSAM mechanism to kill background apps when memory was low.
JetSAM, that sounds intense. So XNU was powering both high-end servers and resource-constrained mobile devices. That's quite a feat.
It really is. And the evolution continued. Mac OS X 10.6 Snow Leopard in 2009 dropped PowerPC support and brought concurrency advances like Grand Central Dispatch and OpenCL. iOS evolved alongside, adding support for multi-core ARM chips and multitasking.
What about later versions of macOS like Mountain Lion and Mavericks? What kind of changes did XNU see then?
Those releases focused on power and memory optimizations. Mavericks, for example, added compressed memory, where inactive pages are compressed in RAM to avoid swapping to disk. It also implemented timer coalescing to reduce CPU power usage.
So XNU was becoming more energy efficient, taking cues from mobile design. What about security? When did System Integrity Protection, or SIP, come into play?
SIP arrived with OS X 10.11 El Capitan in 2015. It's enforced by the kernel's security framework, preventing even root user processes from tampering with critical system files and processes.
That sounds like a pretty significant hardening of the system. What about the file system? When did Apple introduce APFS?
APFS, the Apple file system, became the default with macOS 10.13 High Sierra in 2017. It required kernel support for snapshots, cloning, and encryption at the container level.
And then came the shift to user space drivers with DriverKit, right? That seems like a big architectural change.
It was. macOS 10.15 Catalina in 2019 introduced DriverKit, allowing many drivers to run in user space as driver extensions or DEXTs. This improves system stability and security, as a buggy driver can't crash the kernel if it's outside it.
So that's a move towards a more microkernel-like architecture, at least for drivers. And finally, we arrive at the Apple Silicon era. How did XNU handle that transition?
macOS 11 Big Sur in 2020 was the first release for Apple Silicon Macs. XNU already supported ARM due to iOS, but running macOS on ARM64 introduced new challenges. The scheduler was enhanced to be heterogeneity aware, ensuring high-priority threads run on performance cores, while background threads can be scheduled on efficiency cores to save power.
Heterogeneity-aware scheduling, that's fascinating. So XNU is now optimized for these big little CPU architectures. What about virtualization? How does that work on Apple Silicon?
Apple introduced a new virtualization framework, built on top of an in-kernel hypervisor for ARM64. This allows developers to run Linux or even macOS VMs in user space. However, the open-source XNU code doesn't include the Apple Silicon hypervisor.
So the hypervisor is a closed-source component. That's interesting. It sounds like XNU has gone through a lot of changes over the years, adapting to new hardware and software paradigms.
Absolutely. And it's all thanks to its hybrid kernel design, which combines the modularity of Mach with the performance of BSD.
Speaking of that hybrid design, can you elaborate on how Mach and BSD actually work together in XNU?
Sure. In XNU, the Mach component and the BSD component run as a single kernel entity. They're linked into one binary and share the same address space. There's no Mach versus BSD protection boundary. They call each other via normal function calls within the kernel, not via IPC messages.
So it's not like a strict layering where Mach is completely separate from BSD. They're tightly integrated.
Exactly. Mach provides the core kernel infrastructure and abstractions, like thread and task management, low-level scheduling, and virtual memory management. It also provides the fundamental IPC mechanism. Mach messages sent over Mach ports.
And BSD provides the higher-level services, like file systems and networking, right?
Yes, BSD sits logically on top of Mach and provides the traditional OS personality and services. This includes managing processes, POSIX threads, and the entire set of Unix system calls.
So when a process calls read, does it go through Mach or BSD?
It goes through BSD. The BSD file system code is invoked directly in kernel mode. There's no Mach message to a separate process, as would happen in a pure Mach microkernel system.
I see. So the BSD code executes directly in kernel mode for performance reasons. What about IO-Kit? How does that fit into the picture?
IO-Kit is Apple's object-oriented driver framework. It runs in kernel space but is written in a restricted form of C++. It defines a class hierarchy for devices and drivers. And drivers interact with user space through well-defined interfaces.
So drivers are C++ objects within the kernel. That's interesting. How do they communicate with user space?
They can publish properties accessible via the I/O registry and provide user-client interfaces that allow user space applications to call into the driver in a controlled way.
And what about Mach IPC? Is that still used in XNU, even though it's not used for system calls?
Yes, Mach IPC is heavily used throughout the system for RPC-style interactions and for connecting user space services to the kernel or to each other. Mach ports are the foundation of various high-level features, like the XPC framework.
XPC, that's the inter-process communication mechanism that Apple uses for sandboxed apps, right?
Exactly. Each XPC connection is essentially a Mach port behind the scenes. Mach IPC is chosen for its security model. Mach ports have an associated write system and live in the kernel, so the kernel mediates who can send to whom.
That makes sense. So Mach IPC is used for security-critical communication. What about the scheduler? How does that work in XNU?
XNU's scheduling is rooted in Mach's scheduler, but Apple has modified it significantly over time. It manages threads across CPU cores, supporting SMP, and, on Apple Silicon, asymmetric cores.
Asymmetric cores, that's the big little architecture we talked about earlier. How does the scheduler handle that?
The scheduler is heterogeneity aware, ensuring high-priority threads run on performance cores, while background threads can be scheduled on efficiency cores to save power. It likely uses the thread QoS classes to map threads to appropriate core types.
QoS classes, that's quality of service, right? So threads can be prioritized based on their importance. What about memory management? How does that work in XNU?
Memory management is primarily handled by Mach's VM subsystem. Each task has a virtual address space represented by a set of VM maps and VM regions. Mach's VM is inherently copy-on-write, making fork efficient.
Copy-on-write. That's a classic optimization technique. What about the memory objects and pagers you mentioned earlier?
Mach introduces the concept of memory objects to represent a backing store for memory and pagers, which supply data to those memory objects on demand. In XNU, the default pager, which manages swap files, is implemented by the dynamic _pager user space daemon.
So the pager runs in user space. That's a microkernel design principle, right?
Exactly. It means the policy of how to manage swap space is not fixed in the kernel. By adjusting or replacing dynamic _pager, one could change swapping behavior.
That's pretty flexible. What about virtualization? How does XNU support that?
On Intel Macs, XNU gained the ability to manage the hardware virtualization extensions around 2014. Apple provided a hypervisor.framework API to developers, enabling user space virtualization without third-party kernel extensions.
And on Apple Silicon, there's a new virtualization framework built on top of an in-kernel hypervisor, right?
Yes, but Apple doesn't allow arbitrary third-party hypervisors in the kernel. The hypervisor is part of XNU, but only accessible via Apple's frameworks with proper entitlements.
So security is a key consideration there. It sounds like XNU has a pretty sophisticated virtualization implementation. What about security in general? What kind of security features does XNU have?
macOS uses two complementary isolation mechanisms: secure enclaves and exclaves. The secure enclave is a dedicated, hardened subsystem integrated into Apple's SOCs, used to manage and protect cryptographic keys and biometric data.
And exclaves are a newer security innovation, right? How do those work?
Exclaves further subdivide the operating system's privileges. Instead of having all sensitive operations run in the same privilege domain as the main XNU kernel, Apple is now isolating key resources into separate, externally located domains.
So it's like a defense in-depth approach, where even if the main kernel is compromised, the operations running in exclaves remain insulated.
Exactly. It's all about layering security to protect sensitive data and operations.
Wow! XNU sounds incredibly complex and sophisticated. It's amazing how it's evolved over the years to meet the changing demands of hardware and software.
It really is. And it's a testament to the hybrid kernel design, which allows it to adapt and innovate while maintaining backward compatibility.
So what are the key takeaways from all of this? What makes XNU so special?
XNU offers a fascinating case study of an operating system that is neither fully microkernel nor monolithic, but a judicious mix. Its Mach-based core has proven to be a strength in adapting to new architectures and enabling system-wide features. And the BSD layer ensures that developers and applications have a rich, POSIX-compliant environment.
So, it's the best of both worlds, combining the modularity of Mach with the performance of BSD. It's been a long journey from NextStep to macOS and iOS, but XNU has remained the constant core.
Absolutely, and it continues to evolve, incorporating new techniques to meet the challenges of modern computing. It's a remarkable achievement in operating system design.
Well, this has been an incredibly informative discussion. I feel like I have a much better understanding of Darwin and the XNU kernel now.
I'm glad to hear that. It's a complex topic, but hopefully we've made it a bit more accessible. Thanks for joining me today on this deep dive into the heart of Apple's operating systems. And thank you for listening to Tech Bytes and News. We hope you enjoyed this exploration of Apple's Darwin OS and XNU kernel. Join us next time for more insights into the world of technology. Goodbye. Opening parenthesis. Closing parenthesis.
Bye-bye.